Welcome to Ask and Learn.
In this problem, we have a car that's moving up in an incline with a constant speed of 25 meters per second, and it achieves this speed in 30 seconds. And we want to find the power that this engine supplies during this time frame. We're also given the efficiency of this engine, which is 0.8, and the mass of the car, which is 2 times 10 to the 6 grams, or divide by 1,000 to get 2,000 kilograms. When we're dealing with engines and power, it's important to know that the efficiency of that engine is equal to P out divided by P in. P out is the power that the engine exerts. P in is the power that the engine supplies. And this is what we're trying to solve. So solving for P in, we get P in is equal to P out divided by epsilon, the efficiency of the engine. So we know that P out is equal to the force that the engine supplies times the velocity of the car. Well, we're given the velocity, but we don't know the force that the engine supplies. So to do that, we draw a free body diagram of the car. So the car is at an incline, so that means the weight of the car is straight down. And we know that it has components. So you have Wy in the y direction, and opposite that is a normal force, Fn, and we also have Wx. And we also have, to the right, the force that the engine exerts. So the sum of the forces in the x direction, we get the force of the engine minus the weight of the car, which is equal to mass times acceleration. So solve for F, we get ma plus Wx. So in this equation, we don't know the acceleration of the car, and we need to find a value for the weight in the x direction. Well, for the acceleration, we know that that's just velocity divided by time, and we're given both pieces of information. Velocity is 25, and the time is 30 seconds. So the acceleration of the car is 0.83 meters per second squared. And if we go back to the diagram, we can say sine theta, so this angle right here, is equal to Wx divided by W. So then for Wx, we get W, the weight of the car, times sine theta. So if we plug both in, we get F is equal to W sine theta plus ma. But we don't know the angle of this incline, but we're given a nice little triangle to find that angle. So this is the triangle from the diagram. So 10 at the bottom, 1 on the side. So we can say tangent theta is equal to 1 over 10. So then theta will be tangent inverse 1 of 10. So then theta we get as 5.71 degrees. So now let's plug everything we know to find the force. So we have F is equal to the weight, which is just mass times gravity. So you have 2,000 times 9.8 sine theta, which we know now, sine of 5.71 plus the mass times the acceleration, 0.83. So F, the force of the engine, is 3,606.67 newtons. Now that we know the force, we can find the power supplied by the car. So Pn is equal to this force we just found, 3,606.67 times the velocity, which we know, it's 25, divided by the efficiency of the engine, 0.8. So Pn, the power supplied by the engine, is 112.7 kilowatts. So for the next part of this question, you want to find the average power that the engine supplies for this car. We know that the power average that the engine supplies is equal to the force times the average velocity. And average velocity is just final velocity, which we'll call v2, minus initial velocity, divided by 2. And of course, initially, the car is at rest. So F, the velocity initial, is 0. Well, we know the force and we know the velocity, so we can plug in our numbers. So we got 3,606.67 times the velocity, 25, divided by 2. So the average power exerted by the engine is 45,083.38 watts. So now we can find the average power that the engine supplies. So we'll call that Pn is equal to average power divided by efficiency. So we plug in our numbers. 45,083.38 divided by the efficiency, 0.8. So the average power that the engine supplies, we'll call Pn average, is equal to 56.35 kilowatts.